By the way, this is known as in parallel. When you get the point, when current flows along, it hits an intersection, and then you can go one of two ways. We're now splitting the current, and it will, and I can start at one place, go across each of the resistors independently, come to another place in common, and that's known as in parallel, as opposed to series. So the question is, what happens to the current coming out of the power supply? Increase, decrease, stay the same? I got an increase, you said, decrease, and another decrease right there. Anyone else with an opinion or just a wild guess? Got a whole bunch of decreases. What's that? You a decrease?
Increase.
You're an increase. So far 2 increases and 4 decreases. All right, the next question. Does anyone want to defend increase or decrease?
I'm thinking it'll split and then come back together. Or you'll have 4 amps on the bottom, I guess, square. And then you'll have 2 amps on the top one. And then once they meet on the left intersection, they'll increase they'll add together. But this is my first physics class, so I don't really know. That's my guess.
Say it with more confidence.
Um,
So you can end it with, that's the way it is, so I just.
yeah, that's the way it is.
And anyone who disagrees is looking for a fight.
Yeah.
No, you were supposed to say that, not, you know what? You're absolutely right. It does actually increase the amount of current flowing out of the battery. The question is, why is it that I'm adding a resistor, but I'm increasing the current? Because it seems like if I add a resistor, it would decrease. Well, here's the analogy. We have a fire in the room, hypothetically. There's a fire in the room over here. What are people gonna do? Yeah. Now, Litsy's got more resistance than other people because she's got more tables to have to get around. If she just runs straight, she'll hit a table and bounce. Matter of fact, all of you will hit a table and bounce and then hit another table. If you just went in a straight line and then bounce whenever you hit something, you would eventually make it to the door. If probably 2 people could get through at one time, but if 3 of you tried to get through, you got a little bit more resistance right there. But eventually everyone gets out. If you think of the door frame, how big the door frame is as a sign of resistance. If it's a skinny door, if it's a skinny one, there's more resistance than if it's a really wide one. Suppose you open up a second door over there. A really skinny one, so only a couple people can get through it. But if only a couple people can get through it, those are a couple people who aren't cramming up this way. So what I've done is open up another pathway. It doesn't matter that this is more resistance. It's still, if you think about where this is now over here, right now I've got infinite resistance to get from here to here. No current's going to flow across that, I hope. So what I've done is I've reduced the resistance on this pathway from infinity down to 6 ohms. So my current flowing across here, well, from here to here, I have 12 volts going across here, across the 6 ohm resistor, so I will have 2 amperes on this upper path. The bottom path, I still have 4 amperes. Therefore, I have to have 6 going into it, 6 amperes, and 6 amperes coming out of it. And by the way, these points right here, junctions is the word. They're called junctions. So we have a rule, it's called the junction rule. Whatever current flows into a junction, flows out of a junction. Matter of fact, there's 2 rules, that's one of them. So the junction rule. And also sometimes referred to as the current rule. At any junction, the current flowing in equals the current flowing out. of the loop rule, or the voltage rule. Let's think about that 12-volt power supply. I got a negative and a positive side. As we talked about, the longer side is positive. The shorter side is negative. All I'm saying is that the potential difference from that point to that point is 12 volts. There's nothing about the path that I take. If I start here at the negative point and I move around this way, just through space, end up here, there's a 12-volt difference. I start here and I travel this way, there's a 12-volt difference. I start here and go this way, there's a 12-volt difference. As long as I start and stop at the same place, I've got the same potential difference. And so the loop rule is that the sum of voltages around any complete path is 0. So if I start in one place and end at the exact same place, whatever potentials I gain, I'm going to lose just as many. So if I gain 12 volts going across here, I'm going to lose 12 volts going across there. If I gain 12 volts going across here, this path, I'm going to lose 12 volts going across that path. So if I lose 12 volts going across here, I do voltage divided by resistance, get 4 ohms, 4 amps. Same up here, I get 2 amps, total of 6.
Oh wait, why is it 2 amps?
Because if I gain 12 volts going across here, and I take this path, I'm gonna have to lose it across that. And so it's 12 volts across 6 ohms.
Oh.
And so 12 divided by 6 is 2. Make that 12 volts. Make that 2 ohms. 2 ohms, 12 volts. Nope, that's not what I want. 2 ohms. Right. Just a normal circuit, a series circuit, a parallel circuit. I have 6 amperes flowing out of this power supply. So this will end up with a current of 6 amperes. This will end up with a current of 3 amperes. And that's 12 volts, 12 volts. And here I'll have, since I'll have 6 amperes across that one and 6 amperes across this one, I'll have 12 amperes flowing out of my power supply. So this will drain the battery faster or use up more power, cost me more money than this will. All right, so what happens if there's a break in the wire? What happens to the current?
It stops.
Yeah. The exception is if these wires are close enough, you might spark, because you get this buildup, you get this push of the electrons wanting to jump over to here. So if they're close enough, it will spark, but if it's just a normal break, it won't. So that will stop. Here, if I get a break there, what's going to happen?
Stop.
Here, if I get a break there, what's going to happen?
Continue in the first circuit.
Yeah. So we still get current flowing to this bottom one, the top one's not. And because it is the season, a lot of people are putting up lights. Christmas lights are non-denominational, just people put up lights this time of year. If you have the lights set up in a series, then a light bulb is just, especially the incandescent light bulbs, are just resistors. The classic light bulb are resistors, energy goes through it, it hits resistance, that causes it to heat up. If it heats up to just right, it will glow. That is the essence of Easy Bake Oven. Use the light bulb for cooking because it's giving off a lot of heat and sunlight. So if each of these is a light bulb and you get a break in it, or actually one of the light bulbs blows, all of them go out. If you've got it in a parallel structure, if one of the light bulbs goes out, then only that one goes out, and all the rest of them stay on. Now, the design currently, I guess this is the kind I had growing up. I haven't seen this done extensively, but it does some of it in the fact that you generally get power supply, you get light bulb, light bulb, light bulb, and another strand of light bulb, light bulb, light bulb. And so if that bulb blows there, yeah, I'm gonna lose a string of lights and I don't know which one is blown, but I do have some lights on. And it depends on how picky you are and how much time you have to actually go through and figure out which is the bulb that's blown. Yes?
Which one did you say takes, I missed it, which one did you say takes the less energy?
This one will take less energy because the more bulbs I put into it, the less current will across each of them.
Okay.
And if you put enough in there, none of them will glow. Probably a bad design.
So that would take the most energy, the 6A?
Yes, because each path will have its own current, and yeah, and so if it's designed completely like this, which would be really convenient if one blows, but otherwise, each one is drawing its whatever current is needed, and so if I've got 20 bulbs, I'm using 20 times more energy than if I just had a single bulb. Yeah, also, if you did this design, and so you just kept on tacking them on in parallel, you would end up with just a bunch of wires leading down here. I think that might be prohibitive. Don't forget, if you leave the lights on after Christmas and after New Year's, at some point they become Martin Luther King Jr. Day lights, and then Valentine's Day lights, St. Patrick's Day lights, April Fool's lights.
Or just lights?
I think of them as special, so I would go for a holiday, but you know, you could just call them lights.
So where'd you get the 3 from?
Where to get the 3 from? Because this is in parallel, in series, that would be the equivalent of 4 ohm resistor. And so 12 divided by 4 is 3. Is that good for you? All right. Other questions?
I thought you would want to maybe use less energy so it lasts longer.
So in this circuit right here, I have 6 amperes. Here, I have 3 amperes each. If I put a third light bulb into it, there'd be now 2 amperes flowing across them all. If I had 6, there'd be 1 ampere. At some point, there's not gonna be enough current to get it to glow. So we have that to contend with. Also the nuisance of if one blows, having just gone through. It's in my mind because I just went through a string of lights trying to figure out which one was the bad one. Bruised my fingers. So it's a from a cost point of view, this would be convenient, except for the time. All right. Any questions right now? I think you're ready for a little bit more sophisticated math. Despite what some of you might have just indicated with the head. I got parallel here. We figured out there's 6 amperes flowing through it. That was simple enough. Well, what's the equivalent resistance here? If I have 6 amperes, if I combine these, what is the equivalent resistance? 9.
Are you asking how many ohms?
And as in, if I took these two out and put in a single bulb, or a single resistor, what resistor would that need to be so that the current flowing out of here is the same?
2.
Yes. So if I add these two, the equivalent resistance is a 2 ohm resistor.
Adam?
Ooh, not adding them. All right, because that's 12 volts right there. I'm trying to figure out the equivalent resistance. I know there's 6 amperes flowing out of it. So I have 12 volts and 6 amperes times whatever that resistance is. It's gotta be 2. And yeah, you could probably do it this technique if I gave you this information, but we can go slightly more sophisticated.
So would you divide the 12 by 6 or the 6 by 3?
I divided 12 by 6.
Okay.
Yeah, it's unfortunate that coincidentally it worked out that way. If I took my 2 resistors right there and I just added the reciprocals, 1/6 plus 1/3, what do I get?
1/9.
So if I have them in parallel, I could just add them up. I add up the reciprocals and then take the reciprocal of what I get at the end, and that's the equivalent. So 1 over the equivalent resistance is 1 over resistor 1 plus 1 over resistor 2 plus however many resistors I have. So if I have a 4 ohm resistor and a 3 ohm resistor, and I ask what's the equivalent resistance, first off, they're in parallel. So because once I identify it's parallel, because any current that flows here has a place where it can split. Then I do 1/3 plus 1/4, which is 7/12. And so my equivalent resistance is just the reciprocal of that, which is 12/7 ohms. Questions here? I was going to do a side note, especially for those people who play Scrabble. All right, unit of resistance is an ohm. The symbol is this. There is something known as the reciprocal or inverse resistance, 1 over R. It has its SI unit. The symbol is the upside down omega, and it is the mho. It is a legitimate Scrabble word. It's just ohm backwards. It is equivalent to 1 over n ohm. There's one other word based upon inverse units. There's something called inductance. The symbol is an L, and the unit of inductance, the SI unit of inductance, is the Henry. And there is a unit of 1 over Henry, and it is I've never actually heard it pronounced, but I pronounce it the internet. Just Henry backward. Legitimate Scrabble word. There was a game on Facebook, I think it was Facebook, Prolific. The managed to get that in once. No, Words with Friends. That's what I was doing.
What is the L?
L is just the symbol for inductance. Come on, I got a couple partial letters there, you can't fill in the blanks?
It's a stroke.
I would have been convenient, except for the fact that I was already taken. Yes, Ashley?
The letter next to 1 over resistant E something with the resistant, what's that?
That right there?
No, the one above. No,
Down.
down.
In the middle.
First
All
to
the
the
way to the
left.
left.
1 over R, that's EQ for equivalent. 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus however many resistors I have in parallel.
So what's the thing next to the E?
That right there?
Yeah,
That's a Q.
that's a key.
Are you making fun of my handwriting? Is that-
No.
I thought we were supposed to respect diversities, including illegible handwriting. When I was first learning to make a Q, I made them wrong. It took me a long time to figure it out. I did it kind of like a G, but distorted. Eventually, I figured it out, or saw someone do it and go, oh, okay, that's a whole lot easier. And now it's come down to this.
So with that, would we be able to figure out the voltage?
No, we
Okay.
need either, I would have to tell you the current, a current, or I would tell you, tomorrow or Thursday, we can start out with any questions, and if we take the whole time answering questions, that's fine, and if we don't, then we will talk about magnetism. At this point, any of the stuff that is, any of the electricity stuff, it's either gonna be conceptual or very easy math. Similar to what we basically